All right, today we're going to do something a little different. We're going on a quest to become sound sleuths. We're going to learn how to listen for the secret whispers that materials make right before they break. It's a pretty wild field, so let's jump right in.
Think about that for a second. It's a massive question, right? How in the world can you know that some critical component buried deep inside a huge structure is starting to fail? You can't see it, but what if you could hear it?
Well, the answer is this incredible thing called acoustic emission. You can think of it as the literal sound of stress. When a microscopic crack suddenly forms or a single fiber snaps, it lets out this tiny burst of energy, a sound wave. And our job is to catch that whisper.
Now, like any good detective, we're collecting different kinds of clues. The hit, that's the main event, that sudden snap. The transient data, that's the full recording of the snap, kind of like getting a detailed confession on tape. And to understand the whole scene, we also need status data, the constant background noise, and parametric data, things like temperature, which gives us some really crucial context. Each little clue helps us build the complete picture.
Okay, so before we can even start listening, we have to get our highly specialized toolkit ready. This part is all about setting up our data acquisition program so that we are absolutely sure we don't miss a single critical sound.
The initial setup is a pretty straightforward but totally critical protocol. First, the system finds our hardware. Then, we create a digital case file where all our evidence is going to be stored. Now, step 3, that's the real heart of it. Configuring all our gear. Once that's locked in, we're ready to start listening. And this brings us to a huge fork in the road. Before we even think about pressing record, we have to make a fundamental strategic decision that is going to define our entire investigation.
So what's it going to be? What's the plan? Are we going to be patient, listening only for those very specific snaps and cracks that we think are important? Or are we going to flip on the recorders and just capture absolutely everything, the good, the bad, and the noisy?
This slide just lays it out perfectly, the two different philosophies. On one hand, you have hit-based recording. That's like a patient detective, waiting for one specific clue. It's super precise, it can even pinpoint the source, and you end up with a small, manageable case file. Then you have continuous recording. Think of it like a security camera that's running 24/7. You capture everything, which is awesome for unpredictable environments, but you end up with these massive data files and you lose the ability to locate where the sound came from. So, for the rest of this explainer, we're going to focus on that hit-based strategy, because this is where the real art of being a sound sleuth comes in. Carefully, painstakingly tuning our equipment to pull that one critical signal out from all the background noise.
Okay, listen up. If you remember one single thing, make it this: the detection threshold. The experts all agree it is the single most important setting in our entire toolkit. Why? Because it's the line in the sand. It's what separates those critical whispers from the meaningless background hum.
And this is just a brilliant way to picture it. The threshold is literally a bouncer. Every sound wave walks up to the door, and the bouncer checks its loudness, its amplitude. If it's not on the list, if it's below the limit, it gets turned away. It's not recorded, it's just noise. Only the signals that are loud enough to get past the velvet rope make it into our case file. And the stakes? They couldn't be higher. Set that threshold too high, and you might miss the tiny, critical crack starting to form in an airplane wing. But set it too low, and your data gets flooded with so much noise that you can't find the real clue anyway. It's an incredibly delicate and vital balance.
All right, let's move on to our second most important parameter, the band pass filter. Now, if the threshold was all about loudness, the filter is all about pitch or frequency. It tells our equipment the exact frequency range we want to pay attention to and to just ignore everything else. And this is the perfect analogy. The world of materials is just full of acoustic static. So the band pass filter lets us carefully turn that dial, cutting right through all the other frequencies to lock onto the one specific station where our acoustic emission signals are broadcasting.
Okay, now for a concept that's a little trickier but super important. Rearm time. See, when a crack forms, the sound doesn't just travel in a straight line to our sensor, it bounces all over the place, creating echoes. Rearm time is this clever little timer that tells the system, hey, for the next few microseconds, any sound you hear is probably just an echo of that big event we just recorded. Let's just group them all together as one. But, and this is a big but, this tool comes with a pretty significant trade-off. On one hand, yeah, it cleans up your data beautifully, makes it way easier to analyze. But on the other hand, you risk losing some subtle but important details that might be hidden in those reflections. And worse, if two real events happen really close together, the system might mistakenly lump them into one. So it's a powerful setting, but you have got to use it carefully.
Okay, we've picked our strategy, we've fine-tuned our sensors. Now it is time for the final step. Capturing the raw evidence, the complete sound wave, the material's actual confession.
And this is the job of the transient recorder. As soon as a sound gets past our threshold bouncer, this high-speed microphone kicks into gear to record the entire waveform from start to finish. This gives us the richest, most detailed piece of evidence you can possibly get. And before we hit that big red record button, there's a final checklist. First, do we even need the full waveform? If we do, we have to set the sample rate. That's how many snapshots of the sound we take per second. Then we decide how long each recording should be and whether or not to compress the data. Every single choice here affects the quality and the size of our final evidence file.
The biggest choice right here is how we define that recording length. We can use what's called fixed page length, where we just record for a set amount of time, like, say, 100 microseconds. It's simple, sure, but you might cut the signal off or just record a bunch of silence. Or we can use duration adapted, which is the smarter method. The system records the entire waveform from its start to its end, no more, no less. It's just way more efficient.
So we've walked through all these pretty technical steps, thresholds, filters, recorders, the whole shebang. But let's just take a step back and remember why all this sonic sleuthing matters so much in the first place.
Because it all comes down to this. 1. A single, tiny whisper, captured and analyzed correctly, can be the one crucial piece of evidence. It's the clue that tells engineers to check a pipeline before it bursts, to ground an airplane before its wing fails, or to close a bridge before it collapses. The impact of getting this right is, well, it's immense.
You see, ultimately, this isn't just about data acquisition. It's about learning an entirely new language, the hidden language of our infrastructure. By becoming fluent in these acoustic emissions, we gain this incredible power to understand the health of the world we've built. And by doing that, we can make it fundamentally safer for everyone.
We've developed this incredible ability to listen to the very fabric of our engineered world. And that leaves us with one final fascinating question to chew on. If we can hear our materials, what else should we be listening to?